And now for our final talk, we'll take a deep dive into the internals of GNU Radio that makes all this fun stuff possible. Marcus, do you have your slides already?
Should have prepared slides.
Oh, you don't have slides. Oh, that's even better. Watch me not care.
I can't remember where they are. So they're here.
Ja, steuering L geht hier hoog.
Oh yeah. So thank you for being here. I'm actually quite honored to occupy this oversized slot. So what I want to apologize for in front is that parts of this talk are going to be a bit texty with respect to the slides, which I hope to compensate by talking a lot, which is what I do when I'm nervous. So what we're going to talk about today is, I will have like a 30-second introduction to myself. Then we're going to talk about what actually makes up a GNU Radio program. Then I'm going to talk about what the architectural idea of GNU Radio is. Maybe abstracting a bit. I'm presuming most of you have at least used GNU Radio because you're kind of here. But we'll have to pick up on a few core concepts. Then we'll look at how things are actually implemented. Then I'm going to do something that I really like to do is put my finger in open wounds of GNU Radio. So we'll have to figure out a lot of challenges, and that kind of concludes my talk. What I'm going to do is I'm going to have a few looks at your faces during the talk, and if I see this that I'm a student and I have no idea what's happening here, faces a lot, then I will stop and ask whether you are following me. So please do pretend to be asleep. So who am I? Hi, I'm Marcus. I'm a research assistant at CEL, Communications Engineering Lab, at KIT in Karlsruhe, Germany. I've just started doing my PhD, and I have absolutely, positively no idea what I'm doing. So this is something that I'm not going to talk about very much. I do teach a bit. Not really, I do the exercises. So for, probability, stochastics 101 and comp theory, and some smaller courses. Also, I'm occasionally earn money by freelancing. I've been earning money for some time now at Atos, helping their customers, kind of my customers does. So if you've got a grumpy reply from some support contractor, that might have been me. Also, and that might kind of be the point why I'm here, is I'm maintaining a radio project, which basically means that instead of actually coming to terms with myself and writing some code that fixes some stuff, I'm stuck a lot with deciding what goes in, what doesn't, and why the line endings have to be different or something like that. I don't. So this is a newer development for me, and it's pretty exciting. And I'm still totally overwhelmed by the fact that this is a big project that kind of people from all over Europe come here, and I'm thanking everyone who's been involved with the organization because, wow. So this has really been bigger than I would have imagined. So let's dive into what GNU Radio does. GNU Radio solves a problem, and by solving a problem, it states a problem that it thinks that it's good at, and then it solves that problem. That's a very mathematical thing to do. What is the SDR problem as told by GNU Radio? It's basically, you have some hardware, right? That, I happen to have one. I don't know where that came from. You get some samples from the hardware, then you process these samples, and in the end, you typically get the data out to hardware. Often that hardware is just a storage device, or it's a transmitter or a sound card or whatever. We do that, GNU Radio does that with what it considers high rates, which is a relative term, I reckon. Because these things, I think, on the CPU, 2 megasamples are realistic, let's put it that way. I've just as I said, I've started my PhD, and my professor comes from an optical communications background, and he's like, yeah, I've got this 25 gigasamples ADC. And I'm like, oh, well, that's not a GNU Radio rate. That's not GNU Radio scale. But yeah, so we're not doing that in ASICs. We're doing that on general purpose CPUs, so that kind of is the central problem there, right? We're not designing specific hardware because we're in the business of software-defined radio. So what we're doing is use standard PC hardware to actually deal with signals. So from that stems the flow graph approach, which kind of emulates the idea of having signal processing steps that you just concatenate. So you've probably seen, you've definitely seen, if you've not been asleep during the last 6 talks or so, you've seen a GNU Radio flow graph, and this is one. It's composed of blocks and it has connections. So let's have a closer look at what these blocks, what the elements are and what the constraints are on them. Well, we have blocks, right? These are the things that actually do signal processing. They take digital samples in. We're in the digital world. They have in and outputs. They can have as many or little as they want of each. Due to logical constraints, an input can feed many outputs, but not the other way around. You can only have one output per input. What you as a GNU Radio developer would do is you focus on implementing the signal processing. So you go ahead and say, okay, this is my workload. What I want to have is samples, and I'm going to go ahead and give you samples. So GNU Radio takes care of getting the samples between these blocks exchanged. That's not your job, usually. What you'll have to do is write good code. So that leaves me with the question, where do I put that code? As I said, you put that in a block. What is a block if you really look at it? If you really look at it, a block is actually just a subclass of the C++ class GR block. It's not too exciting. It has, that class has a lot of methods and fields, but most importantly, it has the general work method. And the general work method is where you put your algorithm. So what does it take? It takes 4 parameters, and I'm going to go and manually sort them by importance for the person doing the signal processing. Well, there's the parameter called input items, which is, to a little surprise, your input. It's actually a vector of pointers to the beginning of your input buffers. Why a vector of pointers? Because you might have multiple inputs. So you need some structure to say, okay, this is where the input samples from my first input lay, this is where the second, and so on. Same for the output. So you get some space to put your output. Well, you need to use that, because otherwise you're not producing anything. And because this is, we need to know how much there is of either. There's a vector of available input items, the number of them. So it says, okay, on input 1, there's 100 items. On input 2, there's 2,000 items. And we have a single number called n output items, which is basically just the minimum available space on all your outputs. Okay? So this is a very minimalistic interface for someone who's implementing such stream-based processing. If you've worked with tools like Simulink, you will know that you can do a lot more. And if you worked with tools like SCIA/OSSI/RedHawk, you're probably gone insane implementing Corber interfaces by now. So this is really what I consider the reason for GNU Radio's success is you've got a work function, all it gets is data and how much there is of that. So that's how it looks. The other thing that you're obliged to do is tell GNU Radio, okay, you just called me with this and that many input items, gave me this and that much output space, and I actually made use of that, and I produced so many items by just returning so many. So you just tell the scheduler, and we're going to have a deeper look into what that is, how much you produced. So for completeness sake, there's a few more things that you need to implement. If you're just writing a standard block, you need to have a forecast method. Forecast is a bit boring. It's just, the scheduler goes in and says, okay, I I want you to produce 200 items of output because that happens to be the space that I have available, and I'd like you to do as much work as you could, right? So how much input would you need for that? And you then go ahead and fill in how much input you'd need. This is nasty. You don't actually want to implement that, right? That's boring. It's not part of your signal processing. So for the most common case where the number of items you're going to produce is equal to the number of items that you're going to take, which is like I multiply with a constant. I multiply 2 streams. I filter something. It's always the same input as output. Yeah, we've got subclasses that kind of, conveniently wrap that so that you don't have to care about that. What's really interesting is that GNU Radio has the ability to let you not do work, not do all work at least. Namely, GNU Radio says, hey, I have 2,000 samples of input. What do you want to do with that? And you just go ahead and work on that, but it turns out that your algorithm is just designed to work with 1,024 at the time, for example, because whatever, you do a correlation internally with an FFT that you fixed inside. So you tell the scheduler, hey, I produced only 1,024. And because you're a synchronous block, it knows that that means you've consumed only 1,024. Okay, that leaves us with 954 items, with a lot of items that we didn't consume. Thank you. And GNU Radio is pretty clever about that. GNU Radio just preserves these items. In fact, it leaves them where they are, just remembers to not mark them as consumed yet. So next time you're going to be called, these are going to be, which used to be like the end of what you were presented with as work, is going to be the beginning. So, well, this is your input, this is what you consumed, this is what you've left for the next time, and that's what you presented next time. So this is pretty handy, but it comes with a few architectural consequences that we're going to talk about in a minute. But first, let's talk about how we come from blocks to graphs. So as I said, GNU Radio has this flow graph idea. And that flow graph idea is really like a mathematically defined directed graph. So what's happening there is GNU Radio has classes that you can tell, hey, these are 2 blocks. They do processing. One produces data, the other consumes it and produces new data, and you can connect them. So that's pretty simple, pretty intuitive. You just say, hey, dear top block, I want to connect that signal source to that filter, and from both, please take the 0th output and the 0th input, which happens to be the only ones they have, and then connect the next thing in line. So that gives GNU Radio a definition of a graph, actually as edges between nodes. So that's an abstract representation that GNU Radio keeps until you actually do something with that flow graph. And what does that mean, actually doing something with the flow graph? That means you say, hey, top block, go ahead, do your thing. And yeah, that happens. So GNU Radio goes ahead and analyzes that graph. First of all, it looks at all the blocks in there. These blocks, they define, hey, I'm producing floats, for example, because, well, I'm a real valued processing block. So I tell, I have a property that says my output signature is composed of single items of size 4, because floats on most machines happen to be 32 bits, so 4 bytes. And GNU Radio checks that. GNU Radio tries then to realize all the constraints given by these blocks, which are basically sizes of input items, also output multiples and things, but mostly it looks at whether these item sizes are compatible, and then says, okay, that's nice, let's allocate a buffer that is a multiple of that size. Okay, well, that doesn't tell us much. We only just learned that this means that this arrow here is actually a buffer. Okay, and we know that that buffer is going to be a multiple of 4 bytes in size because 4 bytes is the size of a single item. The moment that happened, we've got buffers representing all the connections in the block. Whereby I must mention that basically every output connection is a buffer. So in my example, I had like this block that has that had one output that went into 2 inputs. That's one buffer. But it has 2 readers. We're going to look at that in a second. And what it also does, and this is the title of this talk, is it starts setting up a scheduling system. And that basically means, okay, there's a thread. So for those not too much into software design on multi-core machines, a thread is simply a thing that can run concurrently or one at a time and is scheduled by the operating system to run on a CPU core. So that's basically all your processes are at least one thread that does some work. So a GNU Radio flow graph ends up with like a single thread for every block that you used. They don't do anything. They're in an idle state. They wait. They don't get scheduled by the operating system so far. What's then happening is that it goes sequentially through all the blocks and tells them, hey, could you, start up, prepare for working? That's an optional step, but your USB servers might want to open that USB transport now, or your audio source needs to talk to someone to actually get like a handle to the audio subsystem. So that's what's happening there. Then GNU Radio does something that's pretty important to the whole causality aspect of things. It basically asks around, hey, who of you is actually ready to work? Because we've got a small problem here. Right? This guy can't do anything because it doesn't have any input data yet. The same for these. What should they consume? At the start of everything, no one produced any data, so there's nothing to be written to this. There's nothing to be displayed anywhere. So the only block whose forecast is going to tell you, yeah, to produce 2,000 items of output, I need exactly 0 input, is a source in our flow graph. So after asking around, GNU Radio realizes, okay, this is a source. I'm going to schedule that one first. Like I'm going to start that one first. And what then happens is, will not surprise you, to be a bit clickbaity here. So let's skip that. Let's not skip that. Let's postpone that. What happens then is that the source block gets notified. Yeah? And that happened because we already asked the forecast method, whether it's ready to produce. It has an empty output buffer, completely empty. So it's asked to produce up to half of that output buffer's size. Why half? Bear with me. That's interesting. So what then happens is, how is it asked? Yeah, actually, the general work function is called. So it actually goes to town and starts DSP. And in our case of our example, the signal source is going to produce samples of a cosine. It's not too exciting, but it just fills the output buffer, or the half of the output buffer that's been offered, with these samples. Then it returns, okay, I actually produced as many samples as you asked me. Fine, says the block executor. That means that something has changed in the vicinity, in the environment of that block. I'm going to notify the adjacent blocks in my graph. So what happens now is that we have the downstream block connected to that source that now gets informed that something has changed. That block now the executor looks at the available input item, says, aha, this has changed. Goes ahead and asks, hey, you have half the output buffer of freedom to produce. You have that much, can you produce with that? The next block says, hey, I'm a sync block. I need as much input as I'm going to produce output. The block realizes, hey, it's just gotten half an input buffer. That is enough, because it's exactly the number of items it's going to produce. So it kicks off the thing. So now comes the interesting part. All the blocks have their own threads, which means that in the situation where, let's look at this, where this one is actually producing the first bunch of items that one produced, the source can start working again. So now we have already achieved parallelism without having put any thought into that. So that's really, really cheap. So the multiply const is presumably a bit faster than the signal source. So while the signal source is still in its second run, the multiply const finishes its first run. So the file sync is notified. The file sync starts consuming these items, starts its own work function, and consumes these items. Now, obviously, files, like storage, is usually a really slow process. Like, we've heard that that can really put a limit on things, and so it's pretty certain that the file sync is going to take longer to finish than the other blocks to work. So while this thing is actually still working, the multiply const might be asked to do like a second run, which still works because half the output buffer is still free. So that's the reason why we're doing half the output buffer, so that there's a guarantee that a reasonably well-behaved block can work in parallel to its predecessor. Yeah, well, that might work, but then we've completely filled the output buffer, right? So we can't go ahead. Because the file sync has not yet returned anything. So GNU Radio knows, okay, all the items there on the input buffer of the file sync are still being used. We can't override them with new output. So that's why I call GNU Radio a back pressure-driven architecture. Basically, there's always some bottleneck in there, and it ripples down. So in this case, the only bottleneck would be the file sync, probably. In Paul's flow graphs, that might have been some resamplers or some filters or filter banks or clock synchronizers, whatever. And then it ripples down, meaning upstream, because buffers are full, can't be used. And of course, as long as I don't produce anything, the downstream blocks get starved, so they don't get any input, they are not called. So that's fine. So what does that come with? Well, that comes with the realization that saying GNU Radio has a scheduler might be a bit of an overstatement. Actually, who's doing the scheduling? That's the operating system. The operating system is in charge of, I notify 5 threads. Who do I wake up first, given that I only have 4 CPU cores? The OS decides that. That comes with a high burden. Well, it comes with a large downside, because the OS doesn't know anything about our data. The OS knows that I've asked it to start, notify one of these threads. So it might be saying, okay, nice, I have this CPU core over there, go and run there. Problem? Let's say we have 2 CPU cores, now 4 CPU cores. The zeros, the first one might be executing the signal source, the second one might be then starting the multiply const, the third one might be the file sync. Is that an optimal solution? Probably not so much, because if you're a bit into general purpose computing, you might know that memory is really rather slow compared to computation. So a multiplication with a constant will take a fraction of the time it would take to actually fill a CPU cache from main RAM. So what's really desirable would be that, well, the signal source and the multiply const basically run on the same CPU core, because that would take I need to keep the data consistent across multiple CPU caches problem away. It would reduce the potential for parallelism, but let's be honest here, very few GNU Radio flow graphs are as simple as that. Most more look like like Paul's flow graph, not like Paul. That would be awesome. So that is something that we need to work with. Another thing that this flow graph architecture really represents very badly is the fact that not everything is a stream. Like the reason people invented why was GNU Radio founded, that was because someone was set up like a little bit, let's say, angry about the Moving Picture Association of America, who introduced a copy protection flag into the ATSC standard. And they were like, this is safe copy protection, we should be like forcing this on every citizen. And Eric was like, yeah, you know, I can go in with SDR and just flip that bit. It's A, not effective, and B, it's like restricting people's freedom. So GNU Radio was actually founded that way. So that was the background that we come from. High rate, for that time, high rate stream processing. But where is GNU Radio in use now? It's used in like physical experiments. Like one of the standard physicist support request email to Atos is, hey, how do I start a sampling on an external signal? Because that's what physicists do. They observe things that typically are finite in length. So that's a very common problem. What's also used for is obviously packetized communications. So one of the, let's say, most popular modules for GNU Radio is the GRIEEE 802.11 module, which implements Wi-Fi, basically, but it does so badly. Why? Well, it's hard to do low latency communications with an external device to a CPU. That's one thing. But if you look at the whole buffers in between here, and I said, like, by default, everyone in here is asked to produce half an output buffer. That's a nice recipe to maximize throughput, because then you can, you know, your algorithm can go in and work on sequential memory. But it's not a good recipe to keep latency in check. So that's another downside. Then, as I said, not everything is a stream. Also, not everything that's relevant to you might be sample data. You might want to say, hey, you know what? This looks like a correlation with my preamble. This is the start of my packet. Please, downstream, please analyze the data stream with respect to that point in time. And so you need to annotate your data stream a bit. So you can do that with tagging. We got these stream tags. And this is where I go into how that's implemented is basically there's a container that contains all the stream tags that are alive right now, and you're presented with a view of these. And that's what you do when you need samples, tags regarding to your samples that you're working now on. You ask a function called getTagsInRange, which is nice, but it comes with a computational overhead because you know there are structures inside that need to be updated with the info, which tags exist on which connection for which samples. And things get really, really hairy as soon as you resample. And they get impossible to solve as soon as you have something that's not like a fixed input to output rate, because then your tag doesn't have a definite position relative to time or to sampling time. So this is a bit harder to get right than, let's say, stream processing. Another shortcoming that we have is, another shortcoming of the stream-based processing problem is, what if, you know, we need some kind of feedback? Everyone knows that, you know, channel estimation should probably go somewhere, modify the state of someone else. And that's not happening here because all we can do is like send data downstream. We can never go back or sidewards. And people have, like in the past, come up with fantastic methods of solving that. They basically said, you know, I can just take a C struct, call yeah, call that an item and push that around, and it's pretty terrible because it's all in line and it doesn't solve the core problem, namely that you can't have feedback. So this is something that I sadly in 2019 still need to show, is that GNU Radio is too stupid to actually do an IIR, a single tab IIR at that. So this obviously doesn't work because the add function can't add two numbers if there's only one input that can possibly have input items already at the beginning. But we could invent some method of saying, okay, there's a second input. We're just not there yet. So this doesn't work. So how do we do feedback? Well, we have a second kind of streams, and these are not actually streams with data samples. They're actually just messages that get sent from one to another block. And they get handled. But how do they get handled? Well, it would be not a good idea if, for example, my channel estimator was updating for some fur filter tabs while that fur filter was still in operation. Especially if that changes the length of the tab vector, because, you know, memory happiness ensures. What was decided was that we added a special step in that scheduling loop where we said, okay, I'm waiting for something to change in my environment, or I get notified, I realize I can actually do work, I do that work. We added a step, check whether there's messages arrived. So that's always kind of thread safe, because it never runs at the same time as the work function, but it's also a hassle, because that was bolted on in 2010, I think. Yeah, and we've had like special edge case problems with that, because now we've got like a system that really is based on a graph, mathematically strictly defined graph that can't have cycles, and thus it's really clear how you shut down something. If something's done, you just tell everyone upstream, sorry, you can't do anything, and everything downstream just finishes doing what it's doing, and then it's done. To something that doesn't have a clear quitting option. There's no exit option there. So this is a disaster. Like architecturally, we broke up a clean design and made it useful. That's what people kind of do, but yeah. So this is one of the core problems that we're facing right now, how to properly do a kind of asynchronous system that still applies to a very strictly defined flow graph. So, another thing that I mentioned a lot was there's input-output buffers. And I also said, actually, there's only output buffers. And how that looks like is, okay, every block has its output buffer or buffers. And every input, yeah, it just reads from that. So there's a small, and also I said that like memory is contiguous. So I'm always presented with, hey, here's your work, here's sample 0 to 20,000, whatever. They lie in memory right next after each other. That can only work under one of two options. First of all, I have infinite memory, which is not even fine if you're a theoretical computer scientist. Or you kind of start switching out buffers, and you know the items that are left over from last call getting copied in first, and copying data is always a bad choice, computationally wise, because I'm blocking memory bandwidth with that, and that's very often the limiting factor. So what GNU Radio does instead is ring buffers. Ring buffers are, well, they're probably one of the first inventions of computer science was like, how do I put something in there to sequentially use it? And it's pretty simple. If you've got like a DSP core, like a digital signal processor, as in silicon, then that will have a address generation unit, and that unit can just do, you give it an address, and it maps it internally to like some modulo size thing, and it works in rounds. That's cool. That works on the, whatever, DSP 86K from the 1980s. not so much on x86. So not so much on ARM. So this is really cool in theory, right? I can just push in samples, and my consumer just takes out samples, and all I have to do is, watch that when producing more samples, I don't reach where I still read, and when reading, I don't overtake what I write. So that's the only two things I have to watch for. Really cool in theory. In practice, sadly not really implementable on commodity hardware. So what GNU does instead is, we kind of abuse the fact that PCs and generally modern CPUs have the feature to map memory. That has a very simple reason, and the reason being is these things have a lot of RAM and multiple programs that should not know of each other's memory. So what's happening is that a computer usually has different kind of addresses, and it has physical addresses, typically an intermediate linear representation of that address space, so that your PC has 16 gigabytes of looking like it's linear memory, and then it got, for every process, its own memory space. So, and what's happening is that the operating system takes some 4 kilobyte page mostly, and just says, okay, dear memory management unit, here's a translation table. When the process asks you for address 0, that's where it goes in actual memory. So that's how it maps memory from actual RAM chips to what your program sees. So different programs see different things at the same address. And that's the cool thing, technically, that allows you to take the same physical piece of memory, 4 kilobyte piece of memory, and map it to different positions. And exactly that's what GNU Radio does. It says, okay, for example, I need an 8 kilobyte buffer. Then I take 2 pages, and I just put them right after each other. So if my workload items happens to be at the end of page 1 and the new ones are at the beginning of page 0, that doesn't look like it's 2 different things. They just look like they're in series, right? So that's really cool, but it comes with 2 main downsides. First of all, I mentioned the granularity. That's 4 kilobyte pages or more. There's really no option to go smaller on most systems. So that means that my buffers need to be both a multiple of 4 kilobytes and of the item size, which is not a problem unless you decide that your output items are 113 bytes in size, because, well, that gets larger. But honestly, it's not that much of a problem because RAM is cheap. What's not cheap is the fact that, well, to be able to freely map memory, you need, your memory needs to be specially handled by the operating system. Normally, your operating system is in charge of mapping memory somewhere, and you can't do that as programmer unless you're kind of a driver or something. So the trick is you ask for shared memory, which is used usually to communicate between different processes, and this is kind of fitting that description actually. But shared memory can't come from a hardware driver because there's no way of enforcing that all hardware drivers adhere to the contracts that shared memory should have. So now we're stuck. Either we can have this nice pseudo-circular buffer, or we can have memory that's directly mapped to your GPU, which would be awesome because maybe your GPU is running CUDA and it's running a FFT on the GPU, accelerating your whole thing. But instead, you need to have a block that just copies, really stupidly copies memory from its input buffer to some GPU buffer, and then from the GPU buffer to an output buffer. That's 2 memory accesses that you really want to avoid in that situation. Even more so if you consider that high-rate data processing often gets samples from network links. So your network card's actually able to put memory, incoming data, where you ask it to, which is awesome, but GNU Radio can't use it. So that's the second thing that we need to change. So, yeah, let's roll with that. Are there any questions here? I see you're ready for the barbecue, so that's actually pretty fine with me. Yeah. To conclude this, okay, GNU Radio has had 18 years of history, which means that a lot of the environmental things have changed. You know, there weren't any any message passing, asynchronous message passing when GNU Radio was invented. There weren't any stream tags. There was no need to put GNU Radio on an embedded device. There was no need to accelerate GNU Radio with a graphics card because, well, that didn't exist back in the day. So, and it would be a lie if I said that every decision that we made on the way was a good one. But, well, we are in a kind of an interesting time right now because the fact is that big money actually comes from big rates. So if people look into, oh, where do I put my corporate money when developing SDR hardware or SDR software, they will typically look into a market that says, okay, we can sell new devices, and that's not happening at a few mega samples, that's happening at a lot of mega samples. And these people would probably want an SDR system that, you know, supports accelerators. That's an interesting time, and I'm pretty confident that we'll sort this out because, first of all, I'm always pretty confident when I'm not nervous. And second, at last GRCon and previous GRCons, we actually had pretty productive talks with people that actually are in the business of building accelerators or building network cards or building high-rate data acquisition devices. So that is happening. It's not just happening in like the coming release. So I already said all this. So what could we do in the near future? What we could do is move away from the I notify everyone when something has changed thing. Instead, and have stream text separate from data and have messages be something completely different than sample data. What we could do is have workload items. Yeah, a workload item is basically the information, hey, this is the function that's going to be called, this is the data that's going in there, and this is the output space that I probably want to use. And then let something clever work out where that space comes from, and use something clever to decide who's going to execute that. And that's the interesting thing is, would be much like web servers do that for the last 25 years, as far as I know. They don't have like one thread per request. They have a worker. And they have as many workers as there are CPU cores. Because obviously you can't do more things in parallel than you have CPU cores, really. So having workers that work on workload items in a queue would be much cleverer. We don't even have to change the buffer architecture for that. We don't have to change any API. We'd just require to rewrite a scheduler. So, while I'm still standing here and talking, I should be coding. What that also brings is the fact that we could be a lot smarter about where to put our workload. As it is now, we just put it on the next free CPU core. But we should be having algorithms that actually look at the data dependency and say, hey, that multiply const block after a compute intense block should just be running right after the compute intense block. There should be things that say, hey, it would be super cool computationally if you could produce 20,000 items at once. But you know, there's a sound card attached to the end, and 20,000 samples, that's half a second. Maybe start with 400. Because, for example, if there's a sound card attached at the other end, the rate's not going to kill your PC at all. So there's a lot of smarts that are missing right now. There's a lot of diagnostics that no one has access to. So that's something that we need to tackle soon. I talked about the buffers already. So that leads me to my conclusion. And I'm way over time, so this is going to be very, very quick. GNU Radio works well. So that's the reason why you're all sitting here, is GNU Radio actually works pretty well, right? It actually scales amazingly well. We abandoned the cleverly designed single-threaded scheduler that built up a whole graph, looked through dependencies, then decided an execution path, called blocks sequentially, because, well, suddenly there were computers with 2 CPU cores, and surprise, badly scaling to 2 CPU cores is still better than scaling well to 1. There's a lot of things that we need to catch up on, but it's really working well at the point. So it's a very universally applicable thing, even if it's not perfectly performing right now. So stick with GNU Radio, it's my first message. Also stick with expecting that things might change in the future. I'm not willing nor expecting that anyone wants to change the basic idea that a block has a work function that takes input buffers and produces output. What I'm willing to expect is that things like forecasts die because no one's willing to actually implement that, because it's like something that's not central to the actual task being solved. So expect changes. If you're in the business of making things go fast, get in touch with me. I'm very interested in things going fast. And with that, I hope I'm open for a few questions, but yeah, I think we might be at the end of the day, so thank you very much for your attention, and I'm open for questions.
As far as I know, there is one Python virtual machine in the whole GNU Radio process. And how is it possible that there is no, that the Python global interpreter lock doesn't prevent several threads from executing concurrently?
So, this, okay, I have to kind of take an excursus here. So GNU Radio is a C++ framework, and it has Python bindings. What that means is basically you can call GNU Radio functionality from Python. First of all, that's super handy when you construct blocks and connect them, because you don't want to do that in C++, you want to do that in a dynamic scripting language. But it also works the other way around. And that's the point here. We can have, for example, GNU Radio calling Python functions. You can even write your own signal processing block in Python. But Python is a bit special as a scripting language. It has, the Python interpreter has one lock globally that avoids that you do stupid things concurrently, like, for example, deallocating memory that someone else might be using still. So, and the point is, yes, there's actually just one Python machine running in a typical GNU Radio system, so that limits the concurrency of Python blocks. I actually don't know whether that's a solved problem. So I must admit that I'd have to look into the gateway block that does all the marshalling, but I think it's pretty possible that there's only one Python block running at a time. But that's not a problem for most blocks, because most blocks, especially these that are concerned with handling data at high rates, are written in C++, and they can run in as many in parallel as they want, as long as they adhere to basic threading decency, which most of all do, which is not all. So I think the gentleman in front, and then, okay.
Yes, is there a way to actually take a high-level look at the GNU Radio graph, and then actually separate it in clock domains, and then actually make one central work function for a complete clock domain?
So yeah, I mean, it doesn't have to be a work function. It can still be a sequence of work calls. But that's basically the idea of the worker model. Is basically you look at the flow graph, you say, this is a path. Graph-wise, this is a path. This is just connected blocks in a row. Would make a lot of sense if I call them sequentially, because then I don't lose the cache locality of the data. So that's exactly where this is going. And honestly, it's happening most of the time in the current scheduling system, because Again, operating systems are awesome. Gotta stress that they are awesome at scheduling things cleverly, but it's all just heuristics. There's no data dependency actually being used in that scheduling.
Okay, thank you for the talk, very interesting. One thing that I've heard, especially from colleagues of mine who like working in data flow kinds of systems, that has prevented many people from using GNU Radio is the dynamic readaptation of the graphs.
So yeah,
and this is something which is very interesting, and many people that I've known have breaking their heads trying to figure out a solution. What do you have to say about that?
That's a good point. So I didn't even touch on that point because it would have taken very long to introduce. But basically, the moment you have like a block set up, GNU Radio assumes that this is the flow graph set up. This is the flow graph that you're going to execute until the end. You start it, and then it's finished at some point. Of course, that's not true. You can say, hey, I want to, disconnect that block, thus disabling the scheduling of that block, and connect a different block. But what you would have to do is like, say, flow graph stop, then everything grinds to a halt, then flow graph connect this and that, disconnect this and that, flow graph start, and everything starts anew. And there's so many problems with that. First of all, like, we make no hard requirements for blocks to actually support stop and start. So this can go very wrong with hardware sources and things. Then we have a lot of problems if we have like this tag position problem. That is already hard when you have a resampler in there. What's your tag position if you're just a freshly connected block? Okay, then we have to reset everything to 0 or what? And the things get really complicated. So this is something that's very inherently hard to solve with the fixed. I notify people when I'm done with my work thing, and everything is relative to the global idea of having a buffer, ring buffer in between. I hope, and I really think this is easier when we have a workload item, because I just stop sending them always to the same guy. I just say, this is the guy I want to send to. And if I want to send things to a different block, I just say, okay, from now on, I send them to a different block. And that's actually how other projects that are very, like, Grass/POTOS actually do that more of the individualistic way. They just send things everywhere. And to be honest, that's a pretty well proven concept, considering that like this is how Ethernet works. And that's one of the reasons that RFNOC has some interesting properties. It does support that, but no one's doing that because it's hard to do with a system that looks like GNU Radio. So yeah. Reconfiguration of flow graphs is hard and not going to be solved with the current architecture.
Any further questions?
Yeah.
No one is asking. I have many questions.
Yeah.
About 3.8, what can we expect?
Awesomeness. Mostly awesomeness. So, bit of background, GNU Radio has been 3.7 point something for, gotta lie, 10 years? No, 10-ish years by now. So there was a bit of a backlog when it comes to architectural things. Often these, like all the changes in 3.8 aren't actually like this deep. There's none of what I sketched here is gonna be implemented in 3.8. Definitely not, because we're in like the final breaths of getting everything working. And we know that most changes will not be breaking the basic principles. What you can expect is, first of all, that a lot of tools get better. We can finally use Python 3. So this is like, my main headache was that Python 2 is so bad in 2019. We get rid of a lot of things that we can't maintain anymore. We used to have WX GUIs, which were actually pretty okay. Problem is that we literally have not a single person who knows how to maintain these. So there was a simple decision. There was Python code. It's not Python 3 compatible. No one knows how it's written. We can't port it to 3.8. So that's gone. What will also happen is that, well, I get very much more aggressive in releasing earlier, more often. That means that as soon as 3.8 is out, we instantly start developing for 3.9, which means that 3.8 will then be a maintenance release that you can use to write your stable software for, and probably should use if you're not planning to do bleeding edge stuff. But it's not like new features will appear in 3.8 anymore. It's like 3.7 at this point. 3.7, we take very much care that 3.7 doesn't break. So most of my maintenance time actually goes into making sure that everything in 3.7 is consistent and I'm not breaking API when patching some bug in 3.7. And basically the promise is that we'll be doing that for a couple of years. Depends on how well 3.8 gets adopted and 3.9 and so on. But yeah, what to expect, 3.8 is really like an incremental release from a user's point of view. From a developer's point of view, it's breaking free. It's basically saying, okay, we don't have to support Microsoft Visual Studio 2002. That means that basically we're much more aggressive in terms of, someone has a cool feature, get it in there for 3.9. So yeah, that's what's happening mostly. So, is there any other question?
Want more?
Yeah, I can do this. Like, an exercise takes 90 minutes, and you're only doing cool questions. So,
thanks a lot. The effort you put in maintaining and all the volunteers.
Well, I'm gonna I'm not the only volunteer in the room. Like, there's people literally organizing a conference here. So, I'll hand that on. Thank you very much.
Yeah, my question is like a lot of implementation we have today, they involve FPGAs because not to get the data rates or the processing speed, we need FPGAs.
Yeah.
That involves like a lot of frictions because it takes like a lot of time to get those things running. So from GNU Radio point of view, what optimizations would you recommend so that we can try to avoid having FPGAs, if possible?
So, there's a lot of things that I'd say to that. First of all, premature optimization is the root of all evil. So really, really, really look at what your flow graph does. Really figure out where your time goes. Is it really the block that you think it is? Often it's not. So get out your tools. Like GNU Radio does have a slightly broken control port, which would usually give you information on, okay, that block used like on average so and so many microseconds per sample to calculate its output. And it in total used so and so many % of the overall CPU time spent by GNU Radio. But what I've really found helpful under Linux is the perf tool, which says, okay, these are the threads that are running. And like basically, or now otherwise, it actually is a sampling system. It looks at the CPU, like it halts, like it interrupts the CPU, says, hey, where's your instruction pointer at now? And then it just bubbles upwards and figures out which function you're in. And then it gives you a rundown of, okay, the work function of the resampler block consumes 80% of my time. So that gives you a good idea that the resampler might actually be the thing that's killing you, and it might be interesting to either optimize that. I'm always open for contributions, or actually get your hardware to run at the right rate. So that's a different thing. Then, yes, there's a lot of friction in the FPGA world. That is a bit inherent to the FPGA world, knowing their tools and their workflows. But there's also, so that's something that I can solve. So what I hope that we can solve is the friction of talking to FPGAs. There's a lot of things that are going on in the interface. As I mentioned, like we need to have flexible data interfaces. But there's also a lot of room for things like, okay, I want to implement something in an FPGA so that it's running faster afterwards. But the first thing I'm going to do is like write a test bench in Verilog or system Verilog so I can test my implementation, which I will later use with my GNU Radio software thing that was super easy to write after having written a super hard to write test bench in a HDL. So what I really hope that will work out is having FPGA or HDL simulation in software as part of what GNU Radio can do. I actually we have more than a test balloon. We actually have a student working full time on that through the Google Summer of Code program. And I'm totally amazed by what he does. Basically, the idea is to use Verilator, which converts Verilog to C++ code. Just compile that, link that in, and then run your simulated Verilog code before you actually put it on an FPGA and get the friction down, at least when it comes to the DSP part. Other questions? Paul wants to ask a question.
No, I just want to end the question session, I guess, because there's other stuff waiting for us, and we certainly can keep asking you questions there, I hope.
Yeah.
So let's thank him for his talk, his work, and all the speakers today.